Okay, this is Doug here again. Here to talk about the Swarm protocol. In particular, what I'm using is it's based on some research that some other folks have done. I know that one of the professors that I went to school, um, he did some work on it, and it mostly had to do with wireless sensor networks, and it's called the LEACH algorithm. Um, Basically, what I'm looking at here, what kind of devices is this protocol used for? The big thing is I'm looking at small devices, robots and things like that. You're not carrying a massive PC, so we're looking at there is some processing power, but there's not a whole lot. And I wanted to make the protocol kind of lightweight enough that it can be easily processed, and so that the AI operations for the robot can be taken care of outside of it, and just make a simply to use library. Takes a couple commands, and the people writing the software for their bots don't have to worry about the implementation about how it's going to communicate um, as a swarm. Uh, and we're also dealing, since we're dealing with robotic devices, they have limited power. And of course, with limited power, you have limited radio range, and we're talking obviously about wireless stuff. So all those things come into play. Now, there's typically like two schools of thought with communications, particularly with networking equipment. And the first one is direct communication, and that's probably about as simple as it gets. And it's basically that every single device communicates directly with the overmind or the central spot or the base station or whatever that you want it to communicate to, but they all have to communicate to it. So, in that scenario, the devices that are furthest away drain their batteries quicker. The radios have to use more power to transmit. There's a lot of retransmits because there isn't enough signal. So, all of that stuff comes into play when you're dealing with stuff that's far away. And one solution to that idea is using what's called the closest communication idea. And that's basically whatever node or robot or bot or however you want to describe it, whichever one is closest to the device that they're all trying to communicate to takes over as a relay so that you can reduce the power that the devices that are furthest away have to deal with. The unfortunate side effect of that is that you take one guy and you overload him with the amount of transmissions that he has to do. So, you're looking at a lot of communications going through one device, in numbered devices. Say if you have 1,000 of them, well, now you have 1,000 devices talking to this guy, which now needs to rebroadcast 1,000 more messages, and that's going back and forth. Obviously, the closest node is going to get its battery drained quicker just because it's busy retransmitting information. And it's going to die out. And then once that happens, it's going to cut off the whole group from communications until the next election cycle, if there is one. So that idea has its limitations. So one solution, at least that I read about, is a compromise. It's essentially an election process that happens where you have a tier system where you have several different nodes that communicate for several nodes within this cluster. And then periodically there's an election cycle that happens. And so the same guy isn't doing the retransmission all the time. So it increases the amount of, you know, there is some increased communications. However, the benefit is that the load is distributed among all the nodes, um, and it can cause the workload to spread a little bit. So, what is the LEACH algorithm? Well, it is a low energy adaptive cluster hierarchy. So, just think of it kind of like a binary search tree, but in the case of this library, it's only got one tier. Um, well, two tiers where the load is shared, and the battery life is used as part of the probability factor in determining whether or not um, a particular node becomes a cluster head and communicates for a smaller group of nodes. So I guess a few things about this library. One, I mentioned briefly, is that it doesn't have multiple tiers. I didn't want this to turn into like this massive, if you know anything about data structures, like a massive binary search tree where you've got two nodes that talk to a node that talk, and it's part of another group of two nodes that talk to another node and so forth. So, you have several levels because that's not really all that beneficial as far as the battery life, because now they spend just as much time communicating back and forth, to reach one particular device. The other thing that is not in this library, and I've given it some thought, is adjustable election cycles. I originally thought, oh, hey, this would be a good idea to see how long the election cycle is based on the number of nodes that are known, plus, processing delay, a percentage of transmission delay as far as the actual network, and of course the growth of the number of nodes in this swarm. The problem with that is that not all nodes will discover all the others at the same time. So if one comes on like a minute later than all the others, um, because they're not constantly saying here I am," which is obviously uh, doesn't, it's well, it doesn't add anything. It just takes battery life for um, you know all these nodes to constantly broadcast that they're alive. And as an example, Bluetooth Low Energy, it does similar things where it spaces out the time for discovery and will kind of go into a sleep mode where things take even longer to discover in order to conserve battery, which is one of the primary goals. The other thing is that I have a limitation at this point of 1,000 nodes, and that again has to do with the uh, not having an election cycle that is dynamic as far as the length used for the election cycle. Um, I may tackle that problem on a version 2 or something like that, where I can try and figure out a better way to do this. But for the meantime, it's a set time period, and the in between cycles is a set time period without real regard to the number of nodes in the swarm. I mean, at this point, I don't have 1,000 devices. The other thing is, and I do have plans to implement these, but my first priority is using IPv6 for communication. And I know, you know, there are a lot of corporations that aren't going to IPv6 yet. They don't really see the need because, well, internally they can just go ahead and use natting, and of course we've already exhausted, at least in North America, we've exhausted the IPv4 space. So I just went ahead and said, you know what, IPv6 supports multicast natively, and and it's used as part of the discovery process for any device that comes on the network. So I'll just go ahead and do that. I will add the IPv4 on a later, say, 1.5 or something like that. And the other thing, of course, is subnet broadcasting, which, okay, you're 1,000 nodes. You're not going to be using IPv4 typically, just because the broadcast space is smaller. And if you try to expand it to hold 1,000 nodes, you have so much traffic between all the ARP requests and all that kind of stuff. Um, Everything is busy just answering ARP requests. And so I thought, I'm not really going to include that. I may just, as a form of feature creep later on, say 1.7 or something like that. And the other thing that's not really included is a fully extensive overmind application. Now, I have written one basically so that you can see basic status of all the different nodes, so you can see when things have come online. Again, though, that uses a different port, and it's got the same setup as far as using IPv6 preferred, IPv4 multicast um, as a later iteration, so that you can at least see, hey, this guy is online, he happens to be a cluster head or not, and if he is, you can at least see which devices he has communication control over. Now, some of the things, because I'm writing this library in Java, the reason why I was writing it in Java is because I was thinking about all the different, subsets that if I wrote it in C, all the different subsets I would need for all the different CPU architectures, and Java just seemed like a almost a no-brainer. Um, of course, there are some considerations here. First off, battery level detection. It's an important part of the protocol. Part of the election process deals with the probability is reduced if the battery is low for obvious reasons. You don't want the guy who's low on juice to be doing communications for a set period of time, say 3 minutes or something like that, while it's low on battery juice. Doesn't make sense to do that. However, if you know anything about Java, you do not have direct access to the hardware. You don't. You have a virtual machine that it runs off of. So Jenny is going to have to be used, and of course it depends on the type of device. Obviously, you have to write your C or C++ libraries to interface with Jenny and to use the methods that are in the class definition so that the battery level can be used. The other thing is link speed detection. Now, I haven't done a whole lot of research on this yet, but I'm faced with the same situation as far as using Jenny, and in this case, I'm actually incorporating XML files for configuration. I know some of you are probably going, yeah, XML. The reason why is it just happens to be a standard, and Java has some libraries that support it well. So I'm using that. You can put in a basic link speed for your stuff. But again, since my background in network IT industry is that when you're dealing with wireless, your link speed drops anyway, depending on how many devices are connecting that to the particular access point that you're accessing. So it's going to drop, it's going to be variable. And link speed, actually, the big thing with the link speed is that I wanted to use it for calculating the election cycle process, as far as the amount of time, and that's based on the amount of nodes, the transmission speed, the processing time. All of that stuff comes into play when you're trying to create a dynamic election cycle for all these nodes. And at this point, I'm just using a static one. I'm kind of constraining myself to, say, 10 megabits with 1,000 nodes, and plus, I guess about 15% transmission delay. And I haven't really calculated what my processing delay will be. I will work on that, of course, but that's part of where I am at this stage in the project. And so that is the latest. I'll give you some drawings on how that works, and you kind of maybe to visualize what's happening and the distances that you're dealing with. Okay, I don't know if I'm doing this right, but I'm trying to give the proper credit for this algorithm. I didn't come up with this. This is something that I read. And it's from IEEE, and it's based on proceedings from the 33rd Hawaii International Conference on System Science in 2000. There are other folks involved on it. There are a number of names. I could present some of the links, but please be aware that portion is not my original work. I'm not claiming it as my original work. I'm just trying to create a library based on that research.